In this video, we're going to learn how to do a Birge-Sponer analysis. So the whole point of a Birge-Sponer analysis is to try and take measured spectra of a real vibrational system, like a real diatomic molecule, and then pull out the parameters of that molecule. So for example, the anharmonicity constant and things like that. So what sits underneath the idea of the Birge-Sponer analysis is that we're going to have a model for the oscillator energies that looks something like this. So this would be the exact energies that you would expect for a Morse oscillator, for instance, where you have the nth energy level is omega tilde times n plus a half, and then you subtract off omega tilde times x tilde all times n plus a half squared. So you have this quadratic term that is the anharmonicity coming in, but the biggest contributor is the omega e tilde. Okay, and so the basic goal now is we want to be able to use what we can observe spectroscopically to determine both omega tilde and omega tilde times x tilde. Okay, and the basic idea of the Birge-Sponer is to, instead of trying to fit this, we turn this into a line problem, and we're going to fit delta G of n, where delta G is, confusingly, this is not the same thing as the Gibbs free energy. We're just looking at the difference between neighboring energy levels. So we look at the energy difference between the n plus 1 level and the n level. That is how we're defining delta G of n. And what we showed previously is that we can write this as omega e minus omega e xe, and then minus 2 times omega e xe all times n plus a half. So we can write this basically as a function of n plus a half. And when you write this, you get a line coming out. The slope of the line will be minus 2 times omega e xe, and the y-intercept will be omega e minus omega e xe. So in other words, if we can take our spectroscopic data, figure out what delta G of n is, plot it against n plus a half, then we can directly figure out each of these parameters that go into the anharmonic oscillator or the Morse oscillator. But what's even cooler is that then we can also take this idea and we can figure out how many bound energy levels there are. So what's the maximum value of n that you can observe? And also you can figure out the dissociation energy d0. Right? We'll talk a little bit about how to do that. The part that might seem a little tricky at first is that we don't actually have delta G of n. This is not what we can measure. What we can measure are just going to be a few different lines that we're calling this omega observed. And in order to get started, what we have to recognize is that these observed transitions correspond to overtones mostly, right? So this first one here, this corresponds to the 0 to 1 transition. We're going to call omega observed 0 to 1. Right, and the second number, the 5,668, corresponds to the 0 to 2 transition. And the last one corresponds to the 0 to 3 transition. Right, so this first one up here this is the fundamental line, this is the first overtone, and this is the second overtone. Right, so what we're measuring again is not these delta G of n's, but what we're measuring are the overtones, or just the direct 0 to n transitions. But we have everything we need in order to figure this out, right? And the reminder that I think helps you see that is that the definition of this omega observed will be, so you have 0 to n, then this is G of n minus G of 0. Okay. And so there are two things that are important in here. One is already, if you look at omega observed 0 to 1, so this one right here, then just plugging in this definition, you see that this also corresponds to delta G of 0 just directly, right? Because delta G of 0, if you plug in this definition over here, this will give you G of 1 minus G of 0, and that's exactly what omega observed 0 to 1 would give you, G of 1 minus G of 0. Okay, so we definitely have the information, and we can get to the other ones, like 0 to 2, by subtracting two different observed lines. And so for example, we have omega observed 0 to 2, and then we subtract off omega observed 0 to 1, then if you plug in the definitions of these, you get g of 2 minus g of 0, and then minus whole thing, g of 1 minus g of 0. And so if you just work this through, you'll see that you have g of 0 minus g of 0. Those two cancel. All that you're left with will be delta g. So let's do this in two steps. So you have g of 2 minus g of 1, and this is equal to delta g of 1. Right? Okay, so what that means is that if we want to figure out these other delta g's, what we need to do is subtract the observed lines from each other, because they both this delta g of 0 to 2 includes information about g of 2. And delta g, or omega observed 0 to 1, includes information about g of 1. And so we just need to subtract them off to figure it out. And so the basic process that you're going to follow when you go to do a Birge-Sponer analysis is you're going to make yourself a little chart. So it's going to look something like this. Make 3 columns. So we're going to keep track of the quantum number n. For good measure, I want to remind you that we are plotting this against n plus 1/2. So we'll make another little column for n plus 1/2. And then we're going to keep track of delta g of n here. All right, so we just go through and we fill this in one by one. So for n equals 0, the first one we can see is n equals 0. That gives us 1/2 for n plus 1/2. And remember, the delta g of 0 is just omega observed 0 to 1. And so we're just going to sort of put that directly in there as omega observed 0 to 1. Okay, and then the next one we'll see is 1. 1 plus 1/2 is 3 over 2. And then this delta g of 1 that we were looking for, we'll get by subtracting this number from this number. Actually, it would be 5,668 minus 2,885.9. So we get I'm going to call it 0 to 2 minus 0 to 1. Then we just keep going more and more like this. For n equals 2, we'll have 5 halves, and this will be 0 to 3 minus 0 to 2. Okay, and if you do this in Excel, it's really quick and easy. You can get all of them done in about 5 seconds. All right, and then you have everything you need, right? So you have the n values. It's going to be when you plot this, this is going to be your x-axis. Then you have your delta g of n. This is going to be your y-axis. So you go through and you go through something like Excel and you just plot each of these points here. And then you fit a line to this data. Maybe it looks something like this. From the fit, you should immediately get out a form that looks like y equals mx plus b. All right, and then from this, you can recognize what the m is. It should be corresponds to this, and what's the b is. It should correspond to what's going on over here. Finally, from where this eventually crosses the x-axis here, you can figure out the maximum. So the n star or the n max, the maximum, the largest quantum number that's still bound for this model. And the coolest part of it, in my opinion, is that then you can actually put all this together. If you integrate the whole curve underneath this, it's just a triangle, so it's a simple integration. Then what you'll get from integrating all of this will be d0. If you put it in the right units, then you'll get d0 tilde, basically in wave numbers. Okay, so that's the outline, and I think you know all the other steps independently. So it's really just a matter of practice and sticking it together.